Hi, this is Dr. John Bergduff. Throughout this course, we've been talking off and on about square roots and principal square roots. But you may remember when we first started talking about those concepts much earlier in the course, I said that for the time being we were not going to look at other types of roots like cube roots and fourth roots, or in other words, roots with other indices. Well, now we need to go back and fill in the blanks a little bit and talk about what those concepts mean. So that's what we will do with this video. So I'm going to start by talking about cube roots. A cube root of a number, A, is a number which, when raised to the third power, equals A. Now that's a lot of backwards and forwards there, and that may not at first glance make a lot of sense, but it is very similar to how we define square roots. If you remember, a square root of a number is a number which when you square it, you get that number. Same idea. So let's take a look at some examples. So let's suppose that we're asked, what is the cube root of 8? Now, what we are simply asking for is what number, when we raise it to the third power, will give me 8. So if this looks familiar from what we did earlier in the course, imagine that number is a box, and you're asking, what do I put in the box so that if I raise the number to the third power, I get 8? What goes in the box? What raised to the third power gives me 8? And with a little looking at it and practicing, you can see that that number is 2. There's no other number that if you raise it to the third power would give you 8. Negative 2 to the third power, that's negative 2 times negative 2 times negative 2 would give you negative 8. So that would not work. The cube root of 8 is 2. Okay. What is the cube root of negative 27? Now you will, I'm sure, remember, as we've talked about square roots for so very, very long, that square roots of negative numbers are not real numbers. So you might be thinking, well, we probably aren't allowed to do this. But again, let's think about, is there a number which, when I raise it to the third power, would give me negative 27? And actually, this will work. You can talk about the cube root of a negative number, and it's a real number. Look at negative 3. Because negative 3 to the third means negative 3 times negative 3 times negative 3, 3 negatives, that would give me negative 27. So square roots of negative numbers were a problem, but cube roots of negative numbers are not a problem. That's interesting. Well, we can talk about other types of roots as well. We can talk about fourth roots, and the definition is very similar. The fourth root of a number A is a number which, when raised to the fourth power, equals A. So, for example, I could be talking about the fourth roots of 16. Uh-oh, the fact that I put an S on that root, that means something suspicious right there. We'll see what that's all about. What we're looking for is a number which, when I raise it to the fourth power, would give me 16. And I think you're going to see that something very similar that happened to square roots. Yes, I can put a 2 in that box. 2 to the fourth power, 2 times 2 times 2 times 2. That would give me 16. But also, negative 2 to the fourth power would give me 16. Negative 2 4 times would give me positive as well. So each number has only one cube root, but 16 has 2 fourth roots, and I really have to list them both. The fourth roots are 2 and negative 2. Okay, that's kind of interesting. In that regard, they act a bit like square roots, don't they? Okay, let's do another fourth root and talk about the fourth root, or maybe it's roots, so I'll just put S in parentheses here, of negative 81. In other words, is there a number which when I raise it to the fourth power would give me negative 81? Now, right away, you can see this is going to be a problem. 3 to the fourth power, 3 times 3 times 3 times 3 would give me positive 81. But getting a negative 81 is going to be a problem because whatever I raise to the fourth power is going to turn out to be positive. I can put negative 3 in here, but 4 negatives multiplied together would be positive, not negative. So this is telling me that the fourth root of negative 81, and this will sound familiar to square roots, I think, is not a real number. So fourth roots act like square roots in a way, and I bet if we look for a pattern there, it has to do with whether the root, the type of root, the index of the root is even or odd. By the way, we're going to just for the time being content ourselves with saying that the fourth root of negative 81 is not a real number. We will find out that just like square roots of negative numbers are not real numbers, but we found a way to represent them in terms of that quantity I. You can represent fourth roots of negative numbers in terms of I as well, but that's a little bit beyond the scope of this course. That's something that you would study in pre-calculus, for example. Let's look at some sort of summary facts here, I think. The bottom line is going to depend on whether the index, the type of the root is odd or even. So let's summarize here. Odd roots of all real numbers, whether those numbers are positive, negative, or zero, are always real numbers. Odd roots of all real numbers are real numbers. Furthermore, each real number has exactly one root of each odd index. So there's not 2 cube roots like there are 2 square roots. There's only one. And we will call that one root the principal root. There's only one, but we're going to call it the principal root. Even roots, a little bit different story. Even roots of non-negative real numbers are real numbers. So you can talk about an even root of a 0 or a positive number, and those are real numbers. But even roots of negative real numbers are not real numbers. And again, what they are, we'll discuss in a later course. Now, each positive real number has 2 roots of each even index, whether you're talking about square roots, fourth roots, sixth roots, eighth roots, so forth. There'll always be 2 of them if you have a positive real number. But one of those roots will be positive, the other one will be negative. The positive of those roots, the positive root, is what we're going to refer to as the principal root. Now, 0 has only one root, and of every index, of every even index, and that root is namely 0. And guess what? We'll call 0 the principal root. Well, that probably seems like a lot of things to keep track of and lots of special cases and different things going on, whether you have even and odd, and when you have even numbers, when you're even roots, whether you're talking about even roots of positive numbers, negative numbers, 0, so many special cases. But with a little practice, it's not too bad. We just have to remember all these special issues. Now, I'm sure you're tired of writing out or seeing me write out the third root of something is something in words. So we have a notation. And this is the notation that you've probably seen elsewhere. Notation. If A is a real number and N is a positive integer, so that'd be 1, 2, 3, 4, 5, 6, 7, so forth. This symbol you see right here is a symbol to denote the principal nth root of A. Now, many people get sloppy, and I probably will slip myself and say that that symbol represents the nth root of A, but it's going to represent the principal nth root of A. That's what we should say, provided that root is a real number. And for the time being, we will just write not a real number when it's not. So in this symbol, I'm going to clean this up a little bit. Well, it doesn't want to clean up. There. Well, no. Okay. There we go. Okay. In this symbol, the different parts of the symbol all mean something or all have names, one of which will be familiar. The quantity under that symbol is called the radicand. The symbol itself that gives you the idea of a root is called a radical, so that's not different from when we were looking at square roots. But the n, the little number that goes right here, is called the index. And the index tells you the type of root, whether it's a cube root or a fourth root or whatever else we might have. Okay, there's sort of a special case when we're talking about square roots, principal square roots, as we have earlier in the semester. We don't write a 2 right here. That wouldn't be inconsistent with the symbol, but when we don't have any index obviously written, that is assumed to be an index of 2, and it represents a principal square root. So that's a special case. Now, just so this doesn't get too crazy and confusing, we want to do some examples of getting used to this symbol, and with a little bit of practice, all the ambiguity will go away. Let's do some examples. So here's an example. Let's look at the principal cube root of negative 27 and talk about it. So first of all, if we're looking at odd roots, we know there's actually only going to be one root, but that's the one we'll call the principal one. It's okay to talk about a cube root of a negative number, so that will be all right too. We simply need to ask ourselves, what number raised to the third power would give me negative 27? And it would need to be a negative number, and 3 times 3 is 9, times 3 is 27. So the principal cube root of negative 27 is negative 3. Here's another one. Principal fourth root of 16. And because we're looking at an even root, but my radicand is positive, this will be a legitimate question. There actually will be 2 fourth roots, but in the spirit of the principal root, we're only going to take the positive one. So we're going to be asking ourselves, what number raised to the fourth power would give me 16, and I only want to pick the positive one. And a little bit of playing around with that, you'll see that that will be a 2. I meant to put a negative 3 up there. So the principal fourth root of 16 is 2. 2 times 2 is 4, times 2 is 8, times 2 is 16. Now, in my definitions, I really only specifically mentioned third roots and fourth roots, or cube roots and fourth roots, but you can have fifth roots, sixth roots, seventh roots, anything you want. The fifth root of principal fifth root of 243 will be no problem. There'll only be one of them. It'll be a positive number. We're asking ourselves the question, what do you raise to the fifth power to get 243? And that might take a little practicing and working around with things, but 3 times 3 is 9, times another 3 is 27, times another 3 is 81, times a fifth one is 243. The principal fifth root of 243 is 3. So I hope that doesn't feel too crazy. A couple more examples. Let's look at the principal sixth root of negative 64. Now, this is an even index, and an even root of a negative number is not a real number. So I don't even have to think about this much at all. If the index is even and the radicand is negative, we simply say this is not a real number. Is this the same thing? Notice here that the negative sign is outside the radical. So we're looking at taking a principal sixth root of 64 and then putting a negative sign in front of it. It's not the sixth root of a negative number. It's the principal square root of a positive number. So we're okay there. Again, there would be two numbers that raised to the sixth power would give you 64. We're looking for the positive one. And just playing with that a little bit, 2 will work. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 is 64. The negative sign in front of the radical simply means that in the final answer we append a negative sign in the front. All right, one more example just to say that you can also look at roots of fractions. Fractions are not always our friends, but they're not really going to be a problem here. Cube root, we're absolutely fine. We're going to end up with a negative number. We're asking ourselves, what do we raise to the third power to give, in this case, negative 8 over 27? And I think you can see that if you have a 2 in the numerator and a 3 in the denominator, that times itself for a total of 3 factors would give me negative 8/27. So the principal cube root of negative 8/27 is negative 2/3. And now that we have talked about roots of other indices, we're going to be able to move in our next section actually into looking at what are called rational number exponents. And those concepts will make sense since we now know a great deal more about roots than we did a little while ago. Take care.